Oftentimes, when students are doing integration by parts questions, there's a few key problems with the way they're doing the question that crop up again and again and again. Students who clearly understand the method, but they're still losing marks. And why is that? It's not because they can't do the maths. I mean, they seem to understand integration by parts. That's not the issue. But it's because they keep on falling into the same traps, and they don't have a clear system for properly doing integration by parts when doing A-levels, whether that be CIE or International Excel or AQA. And following up from the point I made about a lack of a system, part of that is because many students don't even realize where they're actually going wrong, so they keep making the same mistakes again and again and again. So in this video, I'm going to show you exactly what a couple of those traps are. The first one is probably the most important. You can apply that pretty much to the vast majority of integration by parts problems. That's going to be a coherent system that's going to assist you in 80 to 90% even of those problems. And the second one is a bit more high level, but it's a good way to tackle some of the harder type of questions you may get asked by the examiner. So without further ado, let's start with the mistake that costs the most marks. Let's take a real exam style question. And let's say we've got the integral of 2x minus 3 times e to the 2x dx. Now most students look at this and they think, well, let's just pick something. They see e to the 2x, it looks important, so they set u equal to e to the power of 2x. Let's see what actually happens when you do that. So if we let u equal e to the 2x, and we let dv equal 2x minus 3 dx, as a result, we can say that du must equal 2e to the 2x dx, and v, meanwhile, is going to equal x squared minus 3x. Applying the formula then, we get x squared minus 3x times e to the 2x minus the integral of x squared minus 3x times 2e to the power 2x dx. Let's look at what just happened. The new integral is harder than the one we started with. We just went from a linear polynomial times an exponential to a quadratic times an exponential. We made it worse. Now that's 5 to 8 marks on the paper. And if this happens under time conditions, what's going to happen? Well, you're either going to spiral into some messy algebra situation, or you'll probably just abandon the question entirely. So the question now becomes, how do you know which part to choose as u? This is where Lie8 comes in. Logarithms, inverse trig, algebraic, trigonometric, exponential. And it's useful as a rough guide, but here's what nobody tells you. Lie8 is not a rule. It's simply a shortcut to one deeper idea. And that is to choose u so that differentiating it makes the expression simpler, right? So that's it, that's the entire game. It's not a hard set rule, but it's a good general framework to follow in most cases. Let's say we're given the integral of 2x minus 3 times e to the 2x dx. Okay? Now let's apply Lie8. As you can see, a comes before e, so therefore algebraic functions come before exponentials in this ranking. And what is our algebraic function? Well, it's 2x minus 3. So therefore we're going to let u equal 2x minus 3, and we're going to let dv by dx, okay, equal e to the power of 2x. As a result, with u equaling 2x minus 3, du is going to equal 2dx. Meanwhile, with dv by dx equaling e to the 2x, v is going to equal a half e to the 2x. Applying our formula of uv minus the integral v du, we can say that we're going to get 2x minus 3 times a half of e to the 2x minus the integral of a half e to the 2x times 2dx. What does this simplify to? Well, this simplifies now to a half 2x minus 3 e to the 2x minus the integral of e to the 2x dx, which gives us a final answer of a half 2x minus 3 times e to the 2x minus a half e to the 2x plus c. Cleaning this all up, we get a half e to the 2x times 2x minus 4 plus c. And as you can see, when we compare the two answers here, we have the same question. One approach explodes, the other resolves in 4 lines. That's the power of Lie8, okay? So the principle here is to differentiate to simplify. Nothing illustrates Lie8 more concisely than when we have a logarithm involved. So to take the example here, let's say we've got the integral of x squared ln x dx. So if we apply Lie8 to this question, okay, u obviously is going to be ln x. Why? Because it corresponds to L. It's top of the hierarchy. So as a result, du is going to equal 1 over x dx. Meanwhile, okay, algebraic function x squared, that sits in the mid section of our hierarchy. So as a result, a dv over dx is going to equal x squared, which means that v is going to equal x cubed over 3. Okay, so it's easy for me to say Lie8 works, so just do it. But then we wouldn't really get the full intuition behind it. So let's take a look at that via applying the formula itself. As you can see, when we apply the formula uv minus the integral of v du, we get x cubed over 3 ln x minus the integral of x cubed over 3 times 1 over x dx. Now, key point there, we set u, okay, we set u equal ln x from the get-go, which meant that du is equal to 1 over x. Because of that, when we do v du in our formula, it simplifies so much better. Okay, it's beautiful, because as you can see, that 1 over x perfectly aligns with x cubed over 3 to form a simple integral. And what is that simple integral? Well, our formula then goes to give us x cubed over 3 ln x minus a third of the integral x squared dx. From here it's peanuts. It's x cubed over 3 ln x minus a ninth of x cubed plus c. And that's going to be the final answer here, guys. It's going to be x cubed over 3 ln x minus x cubed over 9 plus c. So that is it, guys. As you can see, Lie8 is an extremely powerful framework to be applying when going through about 80 to 90% of the integration by parts questions you'll come across. However, it doesn't work all the time. There are scenarios where you'll do it and you'll get the question completely wrong, so you need to make a few adjustments. Before we go to those adjustments, we're going to go through some other type of problems that you'll come across. So make sure to stay to the end to see when Lie8 doesn't work exactly. Alright guys, just a quick one. If you're enjoying the content so far and you're getting value from it, make sure to hit the link below to join the community me and my team put together, basically designed to help you get an A on A star in A-level maths, because it can be quite tricky. As you can see over here, Furzin, she's done the transformations worksheet that we put together, and she got 100% in that test that she was given. So as you can see, if you're keen to take things to the next level, make sure to click the link below. Okay, so now at this point, we've got a defined system for choosing u. You differentiate to simplify, we get that. Now that handles a huge chunk of what comes up in the paper. But there's an entirely different category of integration questions that can pop up. Not saying it necessarily will, but it can pop up, I think, especially on CIE. So it's worth knowing, especially maybe if you're doing further maths, but it's something to definitely look into as it can catch people out. Specifically, what do you do when the integral looks something like this? Here we have products of powers of both sine and cos. No polynomial, no exponential, no logarithm, just trig multiplied by trig. Most students will just stare at these and have no idea where to start. But there's actually a clean decision tree you can follow, and it really all depends on whether j and k are either odd or even. Take this integral over here. That is the integral of cos to the power 6x times sine to the cubed x dx. Now, you can't just apply integration by parts here. Alright, there's no obvious u and dv split that simplifies things completely. And you definitely can't integrate cos to the power 6x or sine cubed x on their own in a useful way. So what's the move? As hinted at before, the answer to that question depends on an answer to another question. Is j or k odd? Let me show you why that matters, and then we'll solve this step by step. Here's the key insight. If one of the powers is odd, you can simply peel off a single sine x or a cosine x, convert everything else using the Pythagorean theorem, and then substitute. As a result, the lone sine x now becomes part of du. Okay, so therefore everything else is merely a polynomial in terms of u. But this is all very abstract at the moment. So let's get into a proper scenario, an example, so you can see exactly what we're talking about here. Let's take the example of having the integral of cos to the power 6x times sine to the cubed x dx. In this scenario, k equals 3, which is obviously odd. And so what we do here is we're going to peel off one sine x. Okay, so therefore we get sine cubed x is equal to sine squared x times sine x, obviously, and apply the Pythagorean theorem, which means we get 1 minus cos squared x times sine x. As a result, our integral now becomes the integral of cos to the power 6x times 1 minus cos squared x times sine x dx. Moving on from this, if I now substitute u is equal to cosine x, we therefore get du equaling minus sine x dx. So as a result, we get minus the integral of u to the 6 times 1 minus u squared du. Okay, which eventually transforms into negative u to the power 7 over 7 plus u to the 9 over 9 plus c. Substituting that back, we get minus cosine to the power 7x over 7 plus cos to the power 9x over 9 plus c. And that's the final answer here. Clean, no integration by parts needed at all. Here it was simply a substitution, but you need to see the structure. Now, what if j is odd? What happens there? Well, that's fine. Here the same logic applies, just in reverse. Here we're just going to peel off one cosine x, convert again using Pythagorean theorem, so this time we get 1 minus sine squared x, and we're going to substitute u to equal sine x. Now let's take a quick example where j is odd, okay, just to illustrate that point. Let's say we've got the integral of cos to the power 5x times sine to the power 4x dx. So here j is obviously equal to 5. So what do? Well, we're not going to peel off the sine x here, we're going to peel off the cosine x. And when we do that, we get cos to the power 5x is equal to cos to the power 4x times cos x is equal to 1 minus sine squared x squared times cosine x. As a result, if we substitute u equals sine x and du is equal to cosine x dx, we get the integral of 1 minus u squared times u to the power 4 du, which then expands to equal 1 minus 2u squared plus u to the power 4 times u to the power 4 du, which if we expand again gives us u to the power 5 over 5 minus 2u to the power 7 over 7 plus u to the power 9 over 9 plus c. In total, this gives us an answer of sine to the power 5x over 5 minus 2 sine to the power 7x over 7 plus sine to the power 9x over 9 plus c as your final answer. So as you can see, what's happened here? We've simply changed which trigonometric function we're peeling off. The first one where k was odd, we did it with sine x. In the situation where j was odd, we did it with cosine x. And that's when we have at least one odd power, and that can either be k, j, or both. In the event that it's both, we can simply choose to peel off either sine x or cosine x, because either way, the remaining power becomes even. But what happens if neither of them are odd? When neither of k and j are odd, we're forced to ask the question, well, what happens when both are even? Well, when both are even, we can't simply just peel off a sine x or a cosine x anymore, because there's no factor to absorb into du. That's the issue. The entire strategy we just used falls apart completely. So we need something else, a different tool to solve this. Okay, so when both powers are even, guys, our previous identity obviously isn't really going to work here. So what do we do instead? Well, luckily we have an answer. Okay, those are the double angle identities. That's going to help us reduce the powers. And when we do that, we can say that sine squared x is going to equal 1 minus cos 2x over 2, and cos squared x is going to equal 1 plus cos 2x over 2. Okay, these convert powers of sine and cos into expressions involving cos 2x, which, as we know from the simple integrations, we can integrate directly quite easily. Let's take the example of the integral of cos to the power 4x dx. Here, obviously both powers are even. So how do we apply what we just talked about in practice? Well, cos to the power 4x is obviously equal to cos squared x squared. And what's cos squared x? Well, cos squared x, as we've seen before, is equal to 1 plus cos 2x over 2. So therefore we have 1 plus cos 2x over 2 squared. Alright, so if we expand this again, guys, we get a quarter times 1 plus 2 cos 2x plus cos squared 2x. So as you can see, we've got another issue here. And what is that issue? Well, the issue here is that cos squared 2x is still even. And so if we apply the identity again, we get cos squared 2x is equaling 1 plus cos 4x over 2. So, as a result here, guys, what do we get? Well, we have simplified this down. So as a result, we get cos to the power 4x equals a quarter 1 plus 2 cos 2x plus 1 plus cos 4x over 2, which simplifies down to eventually get 3 over 8 plus a half cos 2x plus an eighth cos 4x. Now if we integrate this term by term here, we can say that the integral of cos to the power 4x dx is equal to 3 over 8x plus a quarter sine 2x plus 1 over 32 sine 4x plus c, which means that our final answer, guys, is going to equal exactly that. 3 over 8x plus a quarter sine 2x plus 1 over 32 sine 4x plus c. Before we move on, guys, I want you to quickly note what happened here. What happened here that we had to rectify in order to proceed? Can you guess what it is? Well, here we address one of the most common errors, and that is forgetting to apply the double angle identity a second time. Okay, as you may be able to tell from before, remember we got, even after applying our double angle identity, we got cos squared 2x. Okay, now remember that is still an even indice there, so we had to apply it again to eventually get to 1 plus 2 cos 2x plus 1 plus cos 4x over 2. Then we could integrate. So that's very important. It's a classic mistake. Just because you've applied the substitution once doesn't mean you're out of the woods. You need to make sure that you get it into a form that you can easily apply integration to. So that's just something to watch out for. So just a quick note, guys, a little exam hack. CIE sometimes will ask for the integral of sine squared x, cos squared x, and those types of questions. A good shortcut here is to recognize that sine x cos x is equal to half sine 2x. Okay, just knowing that off the bat will save you a lot of time, so you can quickly plug that in and then square it. It saves a lot of the expanding process. Alright guys, so we've covered Lie8, okay, and we've covered how to integrate products of sine x cos x, as you can see from this decision tree over here, covering when one power is odd, when both powers are even, and when both powers are odd, and what exactly to do in that system. But, as you can recall from before, sometimes Lie8, despite being very useful, is not always a silver bullet. And there are cases where it won't work. So what are those cases? Alright guys, so to take an example, let's imagine we've got the integral of x to the 5 times e to the power of x cubed dx. Now if you apply Lie8, which is a rational thing to do, you're going to get u is equal to x to the power 5. Well, it's algebraic, right? It's going to come before the exponential. That's fair. Meanwhile, dv by dx is going to equal e to the x to the power 3, so therefore dv is going to equal e to the power of x cubed dx. Okay, so naturally, the next part is to integrate dv, which means you're going to integrate e to the power of x to the power 3. Why don't you go ahead and do that and see what answer we get. As you can see, we clearly cannot integrate e to the power of x cubed. There's no closed form for that. So we've been led to a dead end by Lie8. It has failed us. So what do we do now? Take a look at x to the power 5 and e to the x to the power 3 together. And think about it. We've got x to the power 3 there, and we've got x to the 5. So what does x to the 5 actually consist of? Well, it consists of x to the power 3 and x to the power 2. Okay, so we've got two x to the power 3s here in this product. And what else do you notice? Well, the derivative of x to the power 3 is 3x squared, and we also have an x squared here. As a result, if you're thinking what I'm thinking, there's a substitution here hiding in plain sight. Let's let w equal x to the power 3. That means that dw is going to equal 3 to the x squared dx. So what? But what that means, guys, is that x to the power 5 times e to the power of x cubed dx is equal to x to the power 3 times x squared e to the x cubed dx, which means we have w times e to the w times a third dw. As you can see then, our integral clearly transforms into a third times the integral of we to the power w dw. Now guys, it's standard integration by parts. The one we already know how to handle. Okay, it's Lie8 all over the place. Because we're going to say let u equal w. Why? Because it's the algebraic function. I'm going to say dv is equal to e to the w dw. Which means what? Well, that means du is equal to dw. And v is going to equal e to the w. Putting that together, guys, we get a third times the integral of we to the power w dw, which gives us a third of w minus the integral of e to the power of w dw, which we can simplify down to a third e to the w minus 1 plus c. But we're not done yet. Remember what w actually equals. W equals x to the power of 3, which means our final answer, guys, is going to equal a third e to the power of x to the power of 3 times x cubed minus 1 plus c. And that's going to be your final answer. So what's the lesson here, guys? Well, the lesson here is that the skill itself isn't just integration by parts. The meta skill is knowing when to apply substitution and when to apply integration by parts. Okay, it's about recognizing that we don't always have to jump in to Lie8. Yes, it's a good rule of thumb, but it's not always the way forward. In this scenario, we had to substitute before. So as a result, think to yourself just before and say, can I really apply Lie8 here? Most of the times you can, but sometimes, like you just saw, it may not be applicable. So that's something to watch out for.